last topic in Engineering Maths 5, which is double integration. So we've done second order differential equations, Laplace transforms, eigenvalues and eigenvectors, partial differentiation, and now double integration. Again, just like with eigenvalues and eigenvectors, I'm just going to give you the kind of basics, a flavour of what you've got to do in order to answer questions in double integration. It's actually relatively straightforward. It's probably one of the easier topics from Engineering Maths 5. What loads of people forget is their standard integrals from Engineering Maths 3. So it's normally the integration that people forget rather than anything else. Now I will try and avoid using integration by parts and integration by substitution as much as possible and focus on normal integration as much as possible. Right, so double integration is used to find the volume under a plane or between planes in 3 dimensions. Now, obviously double integration means you're going to be integrating twice. Now, rather than integrating under a line like you did in Engineering Maths 3, so you can find the area between under a line or the area between two curves, we're going to be integrating underneath a rectangle or underneath a plane, and that plane is called our region of integration, R. Right, now, so as it says here, R is a region of integration, so that's normally a plane, and dA is either dx dy or dy dx depending on the order of integration. Okay, that totally depends on your order of integration. Right, now, you do it in the order that it looks like. See, if your dx comes first, you're integrating your x first. Then you're integrating your y's. If dy comes first, that means you're integrating your y's, and then you're integrating your x's. Okay? So let's have a look, for example, at this. Right, so I've just laid this out here. So I've got any function involving an x and a y. Right, now, if you can see that there's a dx before a dy, so that means your limits here are x equals, and your dy comes second, so that means your limits in the outer integral are c and d. So what you would do is, you would evaluate this inside integral first. Okay, so you work out this integral here, and then whatever you get as your answer, you're going to differentiate it, integrate it with respect to y, and use these limits here. Now, only the limits of your internal integral, so that bit in the middle, in this case to do with dx, can contain a letter term. Okay, so it can contain two curves, or it can contain numbers. Now, your external integral can only contain two numbers there. Okay, so that's got to be 1 and 3, or 2 and 4. Whereas here, that could be y squared, y cubed, 3y squared, anything like that. These can have letters in them. These have got to be numbers. Right, now, so first thing, right, so see when I'm working out that integral there, the middle one, the internal integral, I just integrate with respect to x, and I treat my y's as if they're constants. Okay, and you treat y as if it's a constant. Okay, then you integrate with respect to y. This time treating no, you won't need to treat x as a constant. Sometimes you might need to treat x as a constant, but remember here, you're only substituting in numbers. So you should only really have y terms in this part here. Okay, so the second integral should okay. So the first part, when we integrate the middle bit, which is with respect to x, because we've got dx first, we integrate the x terms and we treat y's if it's a constant. And then we substitute in our limits of integration a and b. Then we integrate with respect to y. We should only have y terms in our second function after we've done this first bit. And we substitute in our two numbered limits c and d. Right, now, as usual, when you go through the maths and the explanation, it's so much easier when I give you an example. So let's have a look at this. So what we're looking to do is we want to integrate between 1 and 2, the integral between 0 and 3 of 1 plus 8xy dx dy. Now that's the way it would be given to you in an exam or given to you in a question. Right, what I want you to do is, when you get that, just remind yourself that the outside one's y, so I just want you to write y equals 1 here. Right, or just put y equals that, 1's already there. So I want you to change that from being 1, make that y equals 1. And the same thing here, because it's x is in our internal integral, I want you to change that from being just 0 to being x equals 0. Right? Trust me, it just makes things work a little bit better. Now, what I want to do is work out, what does this region here actually mean? So this is y equals 1, that's y equals 2, that's x equals 0, that's x equals 3. Now, y equals 1, if I was drawing it, y equals 1 is just a line that goes along like that. That red line there is y equals 1. Right. Then I'm going to y equals 2. Right, so let's draw that line in. This isn't accurate, that's just to give you an idea of what's going on. That line there is y equals 2. Then here, the line x equals 3. The line x equals 3 is just this line that goes down here like that. So it's just the axis. So, and then I've finally got the line x equals 3, which is maybe about here. So that's y equals 2. That red line that I drew there is x equals 0, and that line there is x equals 3. Right, so the area that are my region for integration is the area that is bound by all of those lines, right? So if I go up the way, my first line is this one here, and my second line is that one there. So it's got to be between these two middle lines here, right? So it can be over here just now or over here just now, right? But it's also got to be between this line here and this line here and my horizontal. So that means that this thing here is my region of integration. So that's your region of integration there. Now, it's relatively straightforward when it's just numbers that we've got here, right? 0 and 3, 1 and 2, but it becomes more difficult when we have curves and letters, right? Now, if you want and you don't really like drawing diagrams, now if you were doing this in an exam, you would need to either be given a diagram or draw the diagram yourself, but let's be honest, most of us have got access to something that could draw diagrams. In the exam, I'll give you the diagram, but what you would do is, if you're doing this for work or in a project or whatever, you would get something up like this software, this website here, it's called Desmos Graph, right? And you might hear me talking about it from time to time. Right now, all I need to do is type in what I've got there. Well, so I had y equals 1, so that's drawing that line for me there. Y equals 2, I'll zoom out so we can see it, so that's up there. X equals 0, and x equals 3. So there we go, there's my region of integration there for me, because that's my bottom bound, my top bound, that's my left hand bound there, that's my right hand bound there. So again, it's this rectangle in the middle that surrounds, it bounds that whole shape. So that's my region of integration. So if you don't want to draw it, just use this Desmos Graph website and that will do it for you. So don't worry about it. You don't need to create an account or anything, it's free. Right, so let's actually work out how to do this integral. I've showed you what the region is, let's work out the integral. So it was the integral between 1 and 2, y equals 1 and x equals 0 and 3 of 1 plus 8xy dx dy. Right, so as I said before, we're going to do this internal integral first, right? So this bit now outside is staying the same. So integral between 2 and y equals 1 and my dy is staying the same. Right, simple as that. Now, we know that when we integrate an integral, we get a square bracket. So I'm going to make a square bracket, and I know that my limits move over to the other side. So that's x equals 0 and 3. And you can write x equals 3 there as well, it doesn't really bother me. Maybe put x for both of them, because otherwise you forget what you're substituting in. Right, so if I integrate this with respect to x, I get x. Now remembering, y's are just treated like a constant, so they just get left there as if they're normal, right? So if I integrate the x part of that, I would get x squared over 2. So that's 8x squared y over 2. Right, so let's keep going. So I'm going to simplify that before I do anything else. Of x, take away 4x squared y between x equals 3 and x equals 0 dy. I should maybe put this square bracket in at the front here as well. Right, okay. Now, I do what I would always do. I've not finished doing this internal integral yet, because when I've got limits, I substitute them in. And it's remember, it's telling me that I'm substituting them in place of x. So that's going to be 3 take away 4 times 3 squared y. In fact, I should have changed that to curly bracket rather than a square bracket because I'm substituting in limits. So the top limit, subtract the bottom limit substituted in, so that's going to be 0 take away 4 times 0 squared y dy. So then that just gives me, so that bit there is just 3 take away 36y, and that whole bit there is just going to be 0 dy. Okay, so that's me done my whole internal integral. I've integrated it, I've substituted in my two limits, and remember it's also subtraction. Top limit substituted in, take away the bottom limit substituted in. Right. Okay, so let's integrate this now with respect to y. Now, as I said in the first bit when I was talking about it, your second integral, when you get to that stage, should only contain the letter that you've got here. Right, so there shouldn't be any x's in this. If there's x's in it, you've done something wrong. Right, so let's integrate it. So that's going to be 3y, take away 36y squared over 2 between y equals 1 and y equals 2. And as again, you can just write 1 and 2 here, but the reason I don't do it is that it confuses me, right? And I'm easily confused, as you know. And he's substituting in the 2. Or you could simplify the 36 over 2 earlier there if you wanted. Makes no difference to me. Leave a bigger gap and make that clearer. Take away 3 times 1, take away 36 times 1 squared over 2. You work that bit out there, and your calculator gives you 78. That bit there gives me 21, so I get 57. Now, double integration yields a volume rather than an area. So rather than units squared, it's a volume, so it's units cubed. So what we've found is we've found the volume underneath that rectangle of that function. Right. Okay. Example 2. Right. We're going to integrate between 0 and 2, 1 and 3, 6x squared y dx dy. Right, so first thing I would do is, well, that should be, well, it's x is inside, so that should be x equals 1. And that should be y equals 0. Just so I make sure that I get my limits right later on. Okay, so what I would do is, I would sketch the graph. So I've got x equals 1 and y equals 0. So this time, my region that I'm integrating over, so that's my line x equals 1, that's my line x equals 3, that's my line y equals 0, and that's my line y equals 2. So the region of integration is this box and here. Right, you can write that down if you want. As I said, it's useful to sketch it later on when the regions get more difficult. So you should always sketch it, right? Because I can see, right, I'm integrating in the x direction between 1 and 3, and I'm integrating in the y direction up the way between 0 and 2. It does get a wee bit more difficult, and you'll see when I do sketches later on why we need to draw the sketch. Right, okay, so let's just do the calculation. So I'm going to do the internal integral first. So that equals, I'm going to write the external one to y equals 0, and so x, so you increase the power by 1 and divide by the new power, and the y stays as it is because you just treat it as if it's a constant, and that's between 3 and 1 dy. Okay? So you substitute in your top limit, which is 3, or you could have simplified it earlier, I suppose. Simplify that again, doesn't really matter. You get the same answer whatever you choose to do it. Dy. Right, so let's simplify this as much as possible. Always simplify before you integrate again if possible. Right, so that's 54. So that's 54y subtract 6 over 3, 2y. Okay, so that gives me 52y dy. Okay, so now we're going to integrate the outside integral. So square brackets now. So that's going to be 52 y squared over 2 between 2 and 0. Substitute in our limits. Or again, you could have simplified this again before you substitute in the limits. Makes absolutely no difference because you've got your calculator to do it with anyway. And if you type that into your calculator, you get 140 with 0. Just 104 units squared. Okay, now what might be interesting is what happens if I try and do the exact same question, but I change the order of integration. So rather than having dx dy, I have dy dx. And that means I swap my limits round. Okay? So let's see what happens with that. Oops. So this is going to have that same region of integration. Right. Okay, so I wanted to do this time integral between x equals 1 and 3, y equals 0 and 2, 6x squared y dy dx. So this is the exact same example that I've just done in question 2 or example 2, but what I want to do is, does it give me the same answer? If it gives me the same answer, Why is that important? If it doesn't give me the same answer, why not? Because surely it should. Right, so as I've said before, I'm integrating over that same region in there. Okay, so that's equal to the integral between x equals 1 and 3 of, so this time I'm integrating y, and x is just a constant, so that's going to be 6x squared y squared over 2 dx, and between y equals 0 and y equals 2 is my limit. Right. So again, you can simplify it first. I suppose I better being quite lackluster with my simplification today. So let's do it. That's meant to be an integral sign. So let's just write that as 3x squared y squared. And then we'll do the substitution. As I said, you get the same answer no matter whether you simplify it just now or you simplify it later on. Simplification just kind of stops you making mistakes, which means I should probably do it more. Right, so now let's substitute in our limits. So that's going to be, and remember it's y that we're substituting in, so that's 3x squared times 2 squared. Take away 3x squared times 0 squared dx. Okay. So this bit here, that's just going to be 4, so that's just going to be 12x squared dx. This bit's obviously just going to give me 0. Right, so that's me integrated that middle bit as much as I can. Right. So let's do that external integral. So I'm integrating with respect to x this time. Let's give me 12x cubed over 3, between 3 and 1. So let's substitute in our limits. That's x equals 1 and x equals 3. Again, I could have made that 4x cubed by simplifying it. It doesn't make any difference. You're substituting in limits, so it doesn't make a difference to what you do. So let's work out what that is. So that's 108. That bit there is 4, which gives us 104 units cubed. And there we go. So if I did dx first, or integrate with respect to x first, I got 104, so that should be units cubed. Before someone corrects me, because it's a volume, remember. And then when I integrate with respect to y first, I got 104 units cubed. So it doesn't make a difference what one you do first. You're going to get the same answer. Now, I just want to show you why that's important. Right, let's look at this example 4. Oh, sorry. Right, let's look at this example 4. Right. Now, I'm not going to finish off this whole example, but I'm going to show you where we run into problems. Right, something's... Right, so I want to integrate twice x e to the power of x y dy dx, and that's y equals 0 and 2, and x equals 1 and 3. So again, that's the same region of integration. I'm not gonna draw it. It's that same rectangle that we're integrating over, right? So I'm not going to draw it, but I just want to show you why the order of integration, your dy dx, can matter. So this time it's dy first, right? So let's compute it. Right, so integrate this with respect to y, right? So that's just staying as it is, because it's not got a y in it. And this bit here, well, it just becomes e to the power of x, y divided by x, because that's our standard integral for the exponential. Because remember, if this was e to the power of 2y, it would be e to the power of 2y over 2. E to the power of 6y, it would be e to the power of 6y over 6. So e to the power of xy is e to the power of xy over x. Between 0 and 2, and remember, put in y equals for at least the internal integral dx, because otherwise you'll get mixed up. Am I swapping in for x? Am I swapping in for y? That's why I always put y in it, the letter corresponding to your limit. Right, so let's work this out. So that's integral between 3 and x equals 1. Now this bit just simplifies down. That just becomes e to the power of xy between y equals 0, y equals 2 dx. Right. So substitute in my 2, so that becomes e to the power of 2x, take away e to the power of 0 dx. Okay, which just becomes e to the power of 2x, take away 1 dx. Because remember, e to the power of 0 is 1. Now that's one of the critical things that we've learned throughout all the maths. Right, now, so now I'm going to integrate it again. So integrate that with respect to x, that just becomes e to the power of 2x over 2. That just becomes x, that's take away x, between 3 and 1. So that just becomes e to the power of 2 times 3 over 2, take away 3, take away e to the power of 2 times 1 over 2, take away 1. Type that into my calculator. So that's e to the power of 6 divided by 2, take away 3. So that's, and there is 198.714. Then e to the power of 2 divided by 3, take away 1. So that's 1.463. whoops, I can't use a calculator. That one there should actually be 2.695. I was wondering why my ones was spelled out. So we get 196.019 or 0.02 units cubed. Right, now what I want to do is do it this the other way, right? So let's have a look at the other way, right? I'll just do it over another page, right? And I'll show you why. So the other way, if we choose to do this next way, which is example 5, so I want to integrate between y equals 0 and 2, the integral of x equals 1 and 3 of x e to the power of x y dx dy, right? Now I'm not going to go through this full example. Now I know if I integrate that, or double integrate it with those, or in that region, my answer is 196.02, because I've done it the other way around, and that's what I know the answer is. So let's just show you why this is a lot more difficult, right? I know what the answer is going to be, or should be, but why is this more difficult, right? So I'm going to integrate between y equals 0, y equals 2, x e to the xy dx. Now that there is a product. Because it's got 2 bits. So the product, in order to do a product and integration, you need to use integration by parts. So what we've done is, by swapping the order of integration, we've made the question far more difficult. So sometimes changing the order of integration makes things easier, and sometimes changing the order of integration makes it more difficult. Obviously, we want to try and avoid using integration by parts because it's where we make mistakes, or avoid using integration by substitution and just use normal integration. Sometimes that doesn't happen. So that's why if I was doing that question, I would try and avoid doing it dx dy. I'd be looking at doing dy dx first. Okay, now if you could do this, I could go through this full example and show you that the final answer is 196.02, but by doing that, I'll probably be wasting a little bit of time. Okay, so let's go on and look at something else. Now, what I said in the description was, sometimes we get calculations or questions where, I'll call this example 5 because that last one wasn't really an example, it was just why it doesn't work, right? And I'm calling this is calculation practice. No, I'm just going to call this a proper example this time, right? Okay, so we're wanting to evaluate between 0 and 2 the integral between x cubed and x of y squared x dy dx. Right, now what's different is that my internal integrals limits are curves or straight line. right? So I've got a curve in here, this x cubed. Before I just had lines that went up and down like that, or and across the way like that, and that meant that was my region of integration. But x cube's a curve, x is still a straight line, right? So let's use my graphing software again, or this Desmos graph thing, to see what my region of integration looks like, right? So I'm going from, remember, it's x is 0 and 2, because they are my outside integrals. So I should maybe rewrite that just so we can make it clear. Okay. So that means that x equals 0, because that's my external integral, and that means that y equals x cubed is my internal integral. So these are both y equals, and those are both x equals. Right, so I'm going between x equals 0 and x equals 2, so that's fine. And then my other ones are x cubed. So x cubed is this function that looks like this, and x, right? So let's zoom in a little bit and have a look. Right, so in fact it was x, it should be x equals 1. I'm going to make this x equals. I'm going to make that x equals 1 in the question. Let me just change that so it makes more sense. Right, it's going to be 1 in the question. Right, so that's the way, that's our question. An integral between 0 and 1 of the integral between x cubed and x of y squared x dy dx. Right, so I've sketched my region of integration, and you can see, right, so I'm going from, along the x way, I'm going from 0 to 1. And then if I'm looking up and down the way, I'm going from this line to this line, right? So my region of integration is this shape here, which is a lot more kind of complicated looking than the rectangles that I've been dealing with before. But it's exactly the same thing. All I'm doing is I'm showing you that these regions can look a lot more complicated. So along the way, it starts at 0 and goes to 1, and up and down the way, it starts at x cubed and it goes to x. Now, if my region is still being given in my diagram as that, I would still use x equals 1, because that's at the end of my region where this is bound. Okay, so let's evaluate this. So integrating with respect to y, so that's going to be y cubed over 3, and x stays the same because it's a constant. And these are my limits, x. So y equals x, I suppose I'll just put y equals in these ones, and y equals x cubed. And I've still got dx on the outside. Oops. Right. So, I'll substitute in my limits. That's going to be, so I substitute x first, that's going to be x cubed times x over 3. Take away x cubed x over 3 dx. Right, so that's going to be x to the power of 4, so that's x to the power of 4 over 3. Take away this one here is x to the power of 10 over 3 dx. So let's integrate these with respect to x this time. That's 10 because 3 times 3 is 9 and 1 is 10. So this time, so I know I've done everything right because I'm left with just x's in my final integral. So that's going to be x to the power of 5 over 3 times 5, which is 15. Take away x to the power of 11 over 3 times 11, which is 33. Between 0 and 1. Scroll down. Right, so that's going to give me 1 to the power of 5 over 15. Take away 1 to the power of 11 over 38. Take away 0 to the power of 5 over 15. Take away 0 to the power of 11 over 33. As usual, you can just write 0 here because you knew the answer is going to be 0. And if I type that into my calculator, I get 2 over 55, I think. 2 over 55 units cubed. Okay, so you're given your region of integration, and that's what we have to do. Now, I want to show you this extra one where there's a little trick in it, and some of the examples in the book on page 9 that I want you to look at might contain a little trick as well. But as I said, you can either draw the graphs or use that Desmos thing to actually see what's going on there. And question 1 is also useful because it shows you what your region should actually be, right? So, this is double integration when the region is described. So this means the limits aren't given to you. You're given this rough description of what the region is that you're integrating over. So I won't say from 0 to 3 and have the integral signs. I'll give you a description. So we should always sketch or use a computer to help identify a region of integration. The description given to you doesn't always give you the correct limits. Right, so you've got to watch that. So this is an example of where, rather than it telling you the limits, the R is described to you, right? So evaluate the double integral over the region R. So that's just telling you that you've got a region, and this time it's telling you to do dy dx. You can do it whatever way around you want, whatever way you think is going to be easiest. Where R is the region bound by the lines y equals x, y equals 1, y equals 0, and y equals 2. Right. So what I would do is I would sketch that, but as I've said already, we live in the 21st century, or most of us do. So let's use that website to do it for us. So y equals, so let's get rid of all we've got so far. I might change that colour off black to make it stand out a wee bit more. Right, so we've got y equals x and y equals 1. X, so y equals x is that straight line there. Right, that looks okay, you'll be able to see that. Y equals 1 is that line there. Right, I might zoom out a little bit. Cool. Right, then I've got x equals 0. 0. So x equals 0 is that line there. And x equals 2. Right. So I'm going to copy that over. Right. Right, now let's talk about this. This is my region of integration. Right? Now, it must be bound by these functions. So, it doesn't start along the way until x equals 0. So it doesn't start till here, I know that. And it definitely finishes at x equals 2. Right, so it can't go beyond x equals 2, and it can't start before x equals 0. Right, now, vertically it can't start until y equals 1. So it can't start till this line, and it stops at this line here. Okay? So it can't start until that line, and it stops at that line. And then it stops at this line here. So that means this thing here, this little triangle here, is your region of integration, right? Right? This bit here is not, because our region doesn't start until y equals 1 and stops at y equals x. This bound doesn't actually yield anything for me, right? So that means that if I look at this triangle, right, my limits for y, so y goes from the line 1 to the line here, x. So it goes up that way, starts there, that's where the bound starts, that's where the bound ends. Right, now, x goes from, now most of you would think it starts at 0 because that's what it says at the question, but it doesn't start at 0 because nothing happens until x equals 1. Right, that's where my region starts. So x goes from 1 to my bound up here, which is 2, because it starts at 1 and it finishes at this line 2. So just imagine you're drawing a line along the way, right? The region starts at 1 and finishes at 2, and those are your x limits. Same with this, like y limits, draw we line up. So it starts at 1 and finishes at this line x. So that means that our integral, and remember that it's telling me to do dy first, but you could do dx first, it doesn't really matter. Let's do dy first though. So I want to do the double integral of x cubed plus y squared y dx. Now see, if I used 0 here, I would get the wrong answer because I'm doing it over the wrong region. Because if I did that, it would involve this little bit here, which is wrong. Okay, so the x, which is the y, which is the internal one, is between y equals 1 and y equals x, and the external one is x equals 1 and 2. Remember, it needs to be that way because the internal integral is the only one that's allowed to contain a letter. Right, so that's the only limit that's allowed to contain a letter, is in your internal integral, and that's why we have to use dy first. Right, this one we can't use dx first. Well, we could, but we need to completely change all our limits and everything, and I'll show you how to do that in the next lecture. Right, so let's do the internal integral. So that's going to be, so I'm integrating with respect to y. So that's going to be x cubed y plus y cubed over 3 between 1 and x dx. So I substitute in my x, that's going to be, and remember these are y equals. So I substitute in my x, that's going to be x cubed multiplied by x plus x cubed over 3. Take away x cubed and 1, take away 1 cubed over 3. So I just substitute in my two limits. Like that. Okay, so let's keep going with this. What's that? X equals 1, wasn't it? My lines are starting to vanish. Right, so integral between 2 and x equals 1 of, that's x to the power of 4 plus x cubed over 3, take away x cubed plus a third dx. Oh, that's line vanished halfway through, so that's in fact a take away. These two are like terms, I can simplify them down. I could now integrate with respect to x, that's going to be x to the power of 4 over 4, take away 2, oh sorry, that should be x to the power of 4, made a mistake there, alright. Been a long lecture, I know. We shouldn't have that many left after this one. So move up the power by 1 divided by the new power, and a third is just going to become x over 3, or a third x, whatever way you want to look at it. And my limits are x equals 1 and x equals 2. So let's substitute those limits in. So that's 2 to the power of 5 over 5, take away 2 to the power of 5, 2 times 2, 2 to the power of 4 over 12, take away 2 over 3, take away 1 to the power of 5 over 5, take away 2 times 1 to the power of 4 over 12, take away a third. And that should give you a final answer, either in fraction form, whatever you want it to be, is 3 and 11 30ths units squared. Okay, so that is double integration. Okay, so the double integration book that I'm putting up on the Microsoft Teams, now there are issues with equal signs and limits and stuff not quite looking the way they should. So normally it's to do with the version of Microsoft Word you're using, but it happens to mine as well, so which is quite annoying. But here's the questions that I want you to focus on. So what I'd like you to do is try worksheet 1, question number 2. So you've got those questions and you've just to do the double integrations and do them in the order that it's telling you to there. Okay, now the answers are at the back of the book, so, and you should obviously get a number answer, such and such units cubed. Now if you want, you can go on that Desmos graph online thing and you can plot these regions if you want, right? So here you've got the triangle, the x-axis and y-axis, that's obviously x equals 0 and y equals 0. and then y equals 2 and y equals 4. A rectangle bound by these lines, so that's less than or equal to, so that just means x equals 2 and x equals 5. That just means y equals 4 and y equals 9. Here again, you've got the x and y axis, that's y equals 0, that's x equals 0, and then you've got that line there, so you could have a look at what that is. You've got a triangle bound by those vertices there, so that's more difficult to draw. You probably have to do that on a bit of paper. So I would kind of leave out D, that wouldn't be anything I would kind of focus on. That's something that we might come to at some point, but it's not going to bother us. And then here we've got the region bound by the equations y equals x, y equals 4x, y equals 3, and y equals 5. And then those there. And just write down maybe what you think the limits would be. But this is the more important stuff here. I'm not, as I said, too worried about getting those regions of integration done. Okay, so tomorrow or maybe later in the week, it depends when I can get this done. I've got loads of marking to do. I know I've got assignment to mark for at least 2 people in this class. I know I said I was going to do it last week. I was so busy that I've not managed to do that yet. But I'll hopefully have another lecture done by the end of this week. And either that or there might be one lecture more than that will be the final lectures on this. Now, as usual, I put up a revision booklet, but obviously because I'm not getting to see you, I'm thinking I'm going to put up a revision video as well, giving you a kind of hints and tips towards how you do some of the stuff in the assignment. Also, the assignment itself is not written yet, so that's something that I need to do also. So I'll hopefully get all these things done over the course of the next week, and I'll get the assignment and all the revision stuff out to you. I think we've got until the middle of June to get this done, but I'm sure if it takes us till the end of June, that's fine, as long as we get it done, because what I don't want you to do is having to do something like some kind of summer school or having extra stuff to do next year when you go to uni, because I know that's happening with a lot of students. So hope everyone's well.